Well, good morning. It's a pleasure to be here today and talk to you about TAKEnergy's technology. I'd like to thank Darcy Partners for this opportunity. So we're focusing on three issues or problem areas that our clients are trying to address. The first is the need to reduce pressure within natural gas systems. The second is the need for power or instrument air for on-site processes. And the third is the need to reduce or prevent emissions for climate change or sustainability targets. Now, existing pressure reduction valves can take care of number one, and there's a variety of generators and air packages out there that can address number two. If you combine solar with those packages, you can also address number two and three at the same time. But by employing TAKEnergy's proprietary vane expander, or our TURVEX system, you can address all three issues within one package. So let me tell you about TAKEnergy and our technology. We have developed and are testing a small-scale radial vane expander to capture energy loss during pressure letdown. Now, what do I mean when I say small scale? This image on the screen is our 10 kilowatt expander, and it's about the size of a basketball. At its core, our unit replaces or supplements existing valves to reduce pressure, but it harnesses energy that's otherwise lost in the process. And because we're using radial vane technology and not turbine-based technology, we've come up with a very simple design with fewer moving parts that utilizes standard bearings and runs at significantly lower RPMs than turbo expanders. We're typically around 1800 RPM for a 60 hertz system. This simple design allows us to bring low kilowatt solutions to an underserved market. Now, many of you are probably familiar with turbo expanders. They've been around for many years, but their sweet spot is with larger systems and at higher outputs. We see a need for expanders in the sub 100 kilowatt range. This image quickly shows where we play in the expander market when you map cost and complexity against power output. So this process flow diagram indicates the typical use case that we would see for our system. Typically, we would utilize a slipstream connection that would allow the customer to maintain their existing pressure reduction system, but we could also be the primary pressure reduction system if required. When the high pressure gas comes into our system, we will go through an emergency shutdown valve and then into our main control valve that throttles our expander based on output required. All of this is controlled by our PLC and control panel, and our expander is simply generating shaft power, which we use to drive a generator. The output of that generator can give you either AC power, DC power, it could be used for auxiliary heat, or it can be used to power an instrument air package. Once the low pressure gas comes out of our system, it's then returned into the downstream low pressure line. So we're currently running a pilot with ATCO Gas here in Calgary at one of their letdown stations. We have about 6,500 run hours to date and are only using about 1 to 2% of the available flow at that station. Throughout the testing, we've been making some adjustments and tweaks to optimize the system, but we have run for 2 months straight at about 4 to 5 kilowatts of output. We've also been running continuous since the beginning of April and plan to do so for the next several months. In terms of specifications, we're taking gas on the inlet side at about 5 to 600 psi and letting that down to about 100 psi. Our flow rates vary based on power output, and we've typically been maintaining power output at around 2.5 to 6 kilowatts, typically even for 4.5 to 6 kilowatts in recent months. The top left picture shows our unit on site, and inside the cabinet, we utilize a divider wall that separates the hazardous gas processing side from the general purpose side where we house our generator and electrical controls. This allows us to maintain Class 1, Division 2 hazardous ratings, as well as general purpose ratings within the same cabinet. And you can see from the pictures on the one side, the top picture, we have our expander. There's the shaft goes through a sealed hole in the wall and is coupled to our generator on the other side. This allows us to maintain the integrity of the hazardous classifications. So one of the things that's worked really well for us with the ATCO pilot is a very robust data capture and logging system. This has helped us troubleshoot and fine-tune performance, allowing us to optimize our design. I've shared a couple of charts here from October last year, which was the month we had 100% uptime. On the top chart, the dark blue line represents ATCO's incoming pressure. The green line shows our RPMs, which has been maintained at a constant 1800 throughout varying pressure ranges, incoming pressure ranges. The bottom chart shows constant voltage in purple. The pink line shows the varying output, which in this case is from about 4.5 up to 6 kilowatts. And then the bottom line shows, the red line shows our frequency in hertz, which has been maintained at exactly 60 hertz, plus or minus 0.2 hertz, which allows us to get within grid spec quality. We're also very pleased to announce that we've just been awarded an additional pilot site for a 25 kilowatt field demonstration unit with Decentralized Energy Canada and the City of Medicine Hat. This system will be located at a natural gas pressure letdown station in Medicine Hat, in the City of Medicine Hat, and that's about 3 hours southeast of Calgary. We will utilize a 25 kilowatt synchronous AC generator that will be grid connected. We're going to be co-located and connected to a grid-scale energy storage system, which will allow us to dispatch power at peak demand times. Our system will provide site power, charge the energy storage system, and return any excess energy to the grid. This will allow us to demonstrate the viability of TAKEnergy's technology as a distributed energy resource and as a microgenerator. We expect to be commissioning and installing in early Q4 of this year. As we look at our plan for commercialization and rolling out this technology, we've just completed our new testing center with support from Alberta Innovates. We utilize a high-pressure, high-output air compressor with several control valves to simulate client field conditions. We'll be able to test new designs and a variety of electrical generators to validate performance within the field. This unit is essentially ready to go, and we will be commissioning this within the next couple of weeks. This is going to greatly enhance our ability to fast-track new designs to the market. Now, we're still working on our commercial product lines, but expect that they're going to look something like this. We envision 3 to 4 platforms or families of products that are easily scalable and customizable to client needs. On the small end, we've received interest in a 100 to 500 watt unit. We see this as an off-the-shelf, plug-and-play type system and would welcome any feedback on use cases for a unit of this size. This also has the potential to incorporate energy storage, and you can see on the first diagram there that we have a number of applications that are in mind for that technology. Our next platform is the Turvex 10K system. This would be a system that would use probably a 2 to 15 kilowatt expander, again with the ability for battery storage and with the applications listed on the screen. The next one up from that would be our 25K system, which would likely house a 20 to 50 kilowatt expander, and again with the application shown on the screen. And then on the larger end, we do see this technology going up to about 100 kilowatts. The commercial designs and pricing are still in development, and again, we would welcome any feedback on this path. So another use case that we've been working on the upstream side is utilizing our system for pressure letdown on the fuel gas feed line for gas-powered compressor engines. We estimate we can get about 5 to 10 kilowatts of usable site power from this. And this also has the advantage of providing relatively clean gas that's feeding the engine. This system could be configured in a way that resembles this process flow diagram. Here I'm showing a chart that indicates what type of power output you can get at different flow rates and different letdown ratios. The relationship between flow and pressure ratio is direct, meaning if you half the flow but double the letdown, you'll get roughly the same output. And so just in conclusion, we've proven the ability of this technology for pressure letdown using clean dry gas in the 2 to 10 kilowatt range. Our Medicine Hat pilot will validate a scaled-up version of our technology, grid-connected and utilizing grid-scale energy storage. We're ready for commercial deployment with utility-grade gas, but are also seeking opportunities to validate with various field gases. I've listed here some additional applications and would welcome any feedback or inquiries on these or other use cases that you may have. So thank you for your time, and I look forward to answering any questions.